In today's lesson, we're going to be looking at how limits can arise when we attempt to find the slope of a tangent line to a curve or the velocity of an object. Now, when you hear some tapping noises, it's just the pen on the whiteboard, and sometimes it takes a moment for me to switch from the arrow to the pen feature, so bear with me on that. Okay, so we're going to be looking at tangents and velocities. Now let's take a look at this question. Find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. So here's our graph of the parabola y equals x squared. And we're looking at finding the slope of this tangent line at the point 1, 1. Well, how many points typically do we need to find the slope of a line? Well, in previous math classes, we've learned that we need 2 points on a line to find the slope of the line. So if we have 2 points on a line, we can just use our slope formula, y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. And then we can find the slope of that line. But since this is a tangent line, we only have 1 point that we know for sure is on the line. This point right here, which is right here, we know this point right there is 1, 1. Now we could estimate a point out here if we wanted to, but we don't have another point on that line, so we can apply the slope formula. So what we're going to do is we're going to estimate the slope of this tangent line. All right. By creating a secant line by choosing another point on the graph of y equals x squared. So let's choose the point 2, 4. And then we could draw a secant line through the point 1, 1 and 2, 4. So here we have our point 1, 1 and the new point 2, 4. Now, if we were just trying to find another point on the graph of y equals x squared, we could have, let me change the color on this pen, if I can. If we wanted to choose some point, we could use the point 2, 4 here. I'm sorry, we could choose the point x equals 2. And we know the associated y value, we could just plug in 2 to our equation, y equals x squared. So we'd get y equals 2 squared, which is 4. That's how we come up with the point 2, 4. Well, now we can use the slope formula to calculate the slope of that secant line. So we plug in the values, 4 minus 1 all over 2 minus 1, we get a slope of 3. Now we could actually come up with the equation to that secant line. We could use the equation of a line y equals mx plus b, and we know the slope of the line is 3, so we can plug that in for our m, the slope of the line. And to find b, we can just pick any point on that line and plug in for x and y and solve for b. So I chose the point 1, 1. Now I can solve for b, which would be negative 2. So the equation of that secant line would be y equals 3x minus 2. How could we get a better approximation for the slope of that tangent line? Of the red secant line, could we choose a point, could be an approximation on the for the slope of our tangent line? May not be a real good approximation, but it would be an approximation. So maybe we'll choose this time x equals 1.5. And notice the slope of this secant line would be a better approximation for the slope of our tangent line. But we could go through the same process. Now we could find the value. If we chose x equals 1.5, our associated y value would be 2.25. And then we could plug that into our slope formula to get the slope of the secant line is 2.5. We then could find the equation of that secant line if we choose to. There's the equation we have so far of the secant line, and then we could choose the point 1,1 to plug in for x and y, solve for b, and we have the equation of that secant line. And the slope of that secant line would be 2.5. Well, we could repeat this process and then choose a point for x closer to 1 on the right side of 1. And notice, we chose, first of all, out here, x equals 2 to create a secant line. Then we chose x equals 1.5, and we had these associated points here. So notice, as the value of x gets closer to 1 from the right, what's happening with the slope of the secant line? Well, the slope of that secant line is getting closer to the slope of that tangent line. So if we draw in that secant line, it would look like this. And you can see the slope of that secant line is even getting closer to the slope of that tangent line. Now, if we wanted to repeat the process of finding the slope of that secant line, we have our slope formula, plug in our values, and we get a slope of 2.2. Now, that would be the table of values showing what we just did, secant line. So if we look at those x values and the associated slopes that we got, our original problem was, how could we find the slope of this tangent line given only one point on the tangent line? Well, we used this secant line, and we looked at the slope of this secant line for different values. And so when we let x equal 2, we created a secant line from 1, 1 to 2, 4. And we calculated the slope, and we found the slope of that secant line was 3. Next, we let x equal 1.5. When we calculated the slope of that secant line, we found the slope of that secant line was 2.5. Then we let x equal 1.2. And remember, we're approaching 1 from the right side of 1. X is getting closer and closer to 1. So here we have 1.2. The associated slope was 2.2. And then if we continued this process, we let x get closer and closer and closer to 1. I'll calculate those associated slopes. Now, we could do the same thing from the other side of 1. We could choose values to the left of 1 and calculate the slope of the secant lines through those points. So for instance, if I chose a value for x of 0.5, now what we're looking at, I'll try to draw this in. This pointer is not real accurate, but let me try to draw it in here. If I drew the secant line now, I'd be going through 0.5 and 1. So I would have this line here. Okay? Now, notice when I chose the values approaching 1 from the right side of 1, let me just draw in that line. Between 1, 1 and 2, 4 here, we had this line. So let's look at the slope of the secant lines when x is approaching 1 from the left side of 1. You can see for x equals 0.5, we get a slope of 1.5. When x is 0.9, our slope is 1.9, and so forth. Now, if you take a look at these values numerically, it appears that the slope of the tangent line is going to be between 2.001 and 1.999. So probably our best guess would be that the slope of that tangent line would be 2. And notice on our graph, looking at this graphically, as we approach 1 from the right, notice the tangent lines are above our, the secant lines are above our tangent lines. And as we approach 1 from the left, the secant line is below the tangent line. And so it essentially squeezes that value of 2 out from looking at those two secant lines compared to that tangent line. Now, let's look at our limit notation that we're going to be using to describe what we've just done. Now, this LIM here stands for the limit. That's the limiting process. Now, look at this piece right here. If we looked at just this piece, M sub PQ, that represents the slope of our secant line. Now here we have as Q approaches P. So remember, let me draw the graph real quick here. When we had our graph looking something like this, we said this was point P here, this was point Q here, and as we let these x values get closer and closer to 1, P was getting closer, or Q was approaching P, correct? So that's what this piece right here means. Q is approaching P. Well, what happens if we found Q approaching P, the slope of that secant line was getting closer and closer to the slope of the tangent line. So if we take the limit of the slope of the secant lines as Q approaches P, we will get the slope of the tangent line. So that's the notation that we will be using when we're working with limits. All right, there's the graph. And let's label some points here. We were looking at that tangent line at the point 1, 1. And let's just call this some point beyond or to the right of 1, x. So we could label that point x, f of x, or f of x is simply x squared. So if we replaced now, if we went in and replaced now in general the slope of a line with what we found for the slope is of the secant line over here, these are just 2 points in general on a graph, we would get this. Because now we would have our x sub 2 minus x sub 1 these points, we know to calculate the slope of the line, the limit of this expression, the slope of the secant line, as f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1, and that would give us the slope of the line through those 2 points. All right, let's use another technique to find the slope of a line at a particular point. Now we're going to use our calculator this time. So we're going to find the slope of the tangent line for this function at x equals 2. Now it appears that this function is y equals 4/3 x squared. Okay, what we're going to do is we're going to use the zoom feature on our calculator. Now that button is just below the screen. It says zoom, and then you're looking for the zoom in key. So after you press zoom, you'll see a blinking cursor when you hit zoom in, and you want to take that blinking cursor to where you want to zoom in around. So move that to where x equals 2 and then go up, touch the graph at that point. Then hit enter and it'll zoom in. So your graph should look like something like this. Now we're going to repeat that process and zoom in again. So you might get something that looks like this. And let's zoom in one more time. We get something that looks like this. Now, what do you notice is happening here? Doesn't it almost look like a line? It makes it look linear since we've zoomed in so many times. Well, how could we use this to help us calculate the slope of the tangent line at x equals 2? Well, since this is almost linear now, if we chose 2 points on this graph, the graph that we have zoomed in on, we're going to choose 1 point to the left and 1 point to the right. Now, I just happened to choose the points. You could choose any points you wanted. However, I'm going to choose the point 1.8. I did the calculation for 1.8, and I know it's not on our graph. It's on the previous slide. So if we looked at the previous slide, I chose this point right here. Let me get rid of this tangent line. I chose this point here, 1.8. Oh, it jumped on me. Let me move back. I chose this point, 1.8, and I wanted to be the same distance on the other side of 2, so I chose 2.2. So this point right here is 1.8, comma, and the associated y value there would be 4. Looking at my y-axis, I realize that the function that we are using is not 4/3 x squared, but it is going to be 1/3 x squared. So this would be 1/3 x squared. So the associated y value would be 1.08. And here at 2.2, we would have an associated value of 1.613. And now if we did the calculation, we would find the slope of that line, which would be an estimate for the slope of our tangent line. We would have, and I'm going to have to write it over our graph here, so we would have 1.613 minus 1.08 all divided by 2.2 minus 1.8, which is approximately 1.3. So our estimate for the slope of the tangent line would be 1.3. So the process was, we zoom in to the point we're trying to find the estimate for the slope of the tangent, so we'll zoom in 3 or 4 times, and then we choose a point to the left of 2, and then moving we'll on to the same distance to the right of 2, and choose those 2 points to calculate the slope. Suppose that a ball is dropped from the upper line between those 2 points, tower which is Toronto, 450 meters above the ground. Tangent line. Find the average velocity of the interval on the interval 2 to 3, and then find the velocity of the ball after 5 seconds. We are going to need to have a little bit more information to solve this problem. So we're going to use the fact Galileo found that the distance fallen by a freely falling body is proportional to the square of the time it has been falling. So that would give us a position of 4.9 t squared. That's the distance that the ball has fallen at any time t. So we're going to be able to use that to help us calculate the average velocity on the interval 2 to 3 seconds, and then the instantaneous velocity. When a problem says after 5 seconds, it means at 5 seconds, at that instant. All right, so for part A, we need to find the average velocity of the ball on the interval. And as we said, part B, we need to find the velocity at a single. Let's look at the graph. Here's the graph of 4.9 t squared. So we have our distance, we have our time, and let's say distance is in meters, I believe it said, and our time is in seconds. So how would we find the velocity on the interval 2 to 3? Well, just as we did in the previous section, we're going to be looking at the slope of a secant line through the points 2, 3. So what we're actually looking at is finding the slope of the secant line between these 2 points. That will give us the average velocity. Well, we can find the associated y value for when x or t equals 2, and we could find the associated y value when t equals 3. So the associated value for distance would be at time equals 2. We would just use our 4.9 t squared. We would get 19.6. Okay, so 19.6. And when t equals 3, we would get a value of 44.1. And now we can find the average velocity between those 2 points. And using a table to find the velocity of the ball at so looking at that calculation, 5, we would get 24.5 meters per second. T approaches 5 from the right. So this first interval here, we're going to create a secant line between t equals 5 and t equals 6. Second, we would create a secant line between 5 and 5.1. Then we'd create the secant line between 5 and 5.05. And we would look at the slope of the secant line, which would be the average velocity. And we're going to see if we're approaching some value as t gets closer and closer to 5 from the right. So looking at the slope of that secant line, it appears that we're getting closer and closer to 49 meters per second. Now, one last item here we're going to look at is, let's just take 2 arbitrary points. The first point we're going to label as A, and then f of A would be 4.9 a squared because we're using that formula that Galileo came up with. And here, we're going to let the distance to a point to the right of A be a distance of h units away. So our second point we could label as A plus h. So labeling that point, we would get a plus h, and then 4.9 times a plus h squared. So if we wanted to find the slope of that secant line through those 2 points, we would have this. Now, when we simplify it a little bit, you can see the a's cancel each other out in the denominator. And this is the form that you're going to become very familiar with. This is the form that we're going to be using to calculate the slope of the secant line through 2 points. Now, what would you anticipate this limit equals? Well, that would be our instantaneous velocity. Again, we're taking the limit of the slope of the secant line as h approaches 0. And this is just a little bit different notation than we used before, but this still is going to find our instantaneous velocity.